Hi, my name is Emily Reeder. I currently lead a data and analytics team at Capital One, and today I'm here to talk about the data error generating process and how our understanding as data movers of the way that data gets made can help fuel better data quality tests and data validation efforts. So imagine for a minute if we were responsible for monitoring the quality of a real world system instead of a data set. We'd probably start by thinking about the common failure modes that we really needed to avoid, like collisions or derailments, and then work backwards from there, thinking about what we need to test to avoid those, like trains not being on the same track or that track itself not being damaged. We wouldn't rely overly on worrying about detecting and testing for low probability events, like all passengers sitting on the same side of a train and it tipping over, or hearkening back too much to industry best practices, like making sure the landing gears don't get stuck, when that's really more of an aviation issue and not really pertinent to our specific focus on trains. And all of this may seem very obvious and very intuitive, and yet I often feel it's not how we approach data quality checks. I often see these exist on two ends of a broad spectrum, either very naive, intelligence-free approaches that really tie back to basic database integrity checks like nulls, duplicates, primary and foreign key relationships. On the other end of the spectrum, we have some really advanced, very clever artificial intelligence techniques using things like anomaly detection and the tracking of statistical properties. But I argue there's a real opportunity and a real gap in the middle when it comes toward to bringing more human intelligence and a hypothesis-driven approach to data quality. And again, we as data movers are actually the best suited to do this because we're the ones that have the best perspective of every step in the data lineage, all the way from the real world where it's created, that collection, its loading and movement between systems, and its final transformation once it's landed in our warehouse. And I argue that with two very simple questions, we can actually get a lot more power out of our tests. First, we can ask ourselves, what do we need to be true in that last mile of data transformation to ensure that we're producing correct data sets and analytical results? And knowing that, what are all of the liabilities, what are all of the potential breaks all of the way up this value chain that could actually cause those things from not being true? And I think these two questions really help us focus our attention better. I'll take an example of the many different ways that data can fail to load. Obviously, we'd all prefer to have nice, complete data sets, but we know there are a lot of ways that data loads can break down. Data can go stale and stop loading. It can do that for a full day, or maybe a partial day. A load can partially work and then fail. Sometimes if we're loading data from multiple sources, some of those may come through, others may not. We can have missing data where data went stale and then was fixed and resurrected, but not backfilled, or maybe we even loaded data multiple times. Now, a standard recency check, such as checking the maximum date of the data set, actually only catches one of these many forms of missingness, one of these many forms of loading errors, but without actually reasoning about how our data can go missing, what might have broken, we might be happy just doing that basic recency check instead of something more advanced. So with that kind of conceptual framework in mind, I want to take an applied example from the New York subway system ridership data. And to give you a little context on the data generating process for this data set, data is collected at every single turnstile throughout New York City, and it's done so by every single turnstile, recording the cumulative number of times it's been turned and uploading that information to a server 4 times a day. So we have this really nice panel data structure of every turnstile at every point in time. If we wanted to calculate system-wide metrics, we might have a transformation layer to our data set that looks something like this. We'd take that data for every single turnstile. First, we could back out those cumulative number of entries to the number of entries for a specific time period by doing a lag difference. And then finally, we could aggregate that up to any level of granularity of interest, such as the station level or even the system level. But even this very basic set of data transformations does make some pretty critical assumptions. First, we're assuming all of our data is non-missing, or else that lag function will break. And we're assuming that the monotonicity really holds for every single turnstile. And without that, we'd really risk having some big misses in doing these transformations blindly. So knowing that those are our key risks, we can start thinking about how we need to test our data to ensure those things are true. To avoid missing data, we'd want to be thinking about missing data can occur if sensors break, or if somehow they lose the connection to their server to upload the data. Similarly, we could end up with non-monotonic data, non-increasing, if that sensor is broken and it starts to somehow record the inflowing traffic incorrectly, or maybe if it's replaced altogether and reset to 0, perhaps during maintenance. And so you can see as we talk about these ideas, a common thread is that those sensors and those points of collection are really the keys that we need to figure out how to test around. And this inspires ways that common data tests that we already use can be tweaked ever so slightly to get a lot more power out of them. And one way I find particularly useful for doing that is by using group checks. So applying many of the same checks like uniqueness, maximums, minimums, but instead of doing it at the aggregate dataset level, doing it by individual group or partition of data. Some tests are actually only expressible in this way. For example, a turnstile ID might not be unique across all of New York, but it should be unique within each station. Other tests are simply more rigorous. Like we were talking before with missing data, a maximum date is maybe somewhat underpowered, but checking the maximum date of every single turnstile individually could add a little more oomph. And finally, other times it's just a little more semantically intuitive to think this way. So applying these sorts of group checks, we can see what we find in the New York subway system data. For monotonicity, this is really only expressible by group. When we braided all the turnstiles together, we can't expect the entries variable to be monotonic, but we should for every single turnstile individually. Ideally, we'd love one turnstile to have a trend that looks like this, and every single turnstile in our data set to have a trend like this, various slopes, various levels, but same pattern for all 5,000 roughly turnstiles in this station. But in reality, when we conduct these sorts of tests at the group level, at the actual level of the data generating process, we find some interesting anomalies. Sometimes the trend goes up as we want. Other times it universally trends down because the turnstile is counting in the wrong direction, or we can find this oscillating pattern for turnstiles that are reset frequently due to maintenance events. Similarly, we can find examples of cases where we do get more rigor in our tests by doing them at the group level. There's no combination of date and timestamp that's universally missing in the New York subway system data, but if we actually drill down to those turnstiles, we can find that between 50 and 100 turnstiles are missing records at really any given point in time, which again can pose some really serious challenges as we're doing that transformation. So in summary, by asking these two core questions, what do we need to be true? And what throughout this whole data value chain might prevent that from being true? What might, so to speak, get our data off the rails can really help us structure better quality tests that are more likely to identify core risks. And if I've convinced you that group checks in particular are useful, I'll briefly mention that now those are available in the DBT utils package for those that use DBT due to a pull request that I submitted and was approved earlier this year. So for many of the common data tests that you use in DBT, you can now simply add a group by dimension by editing that YAML file and just adding the columns you want to group by to really drill down and get these more granular tests using the same frameworks, the same mindsets that we're already familiar with. So thank you very much for your time. Really appreciate the talk. If you want to get your hands on this data or read more about these ideas, I've linked both to code and different blog entries I've written on the last slide of my deck. Thank you.